How does temperature affect matter? Okay, let's see. If something is at a low enough temperature, what state of matter will it take up, or will it form? Huh? If you get the temperature low enough, all substances will become a solid. Well, liquid within a solid, yeah. So solid. Okay. Raise the temperature, you get what? Raise the temperature. You got this solid, you're going to raise the temperature. Starts to melt, so it becomes a liquid. Okay. Raise it some more.
It'll be gas.
Okay. Turns out there's actually more than one form of a solid. There's a crystalline solid, and there's an amorphous solid. Okay? We'll come back to that in a minute. All right. Okay, observable behavior. All right, so I'll make a column here for observable behavior. When we observe a solid, how do we know it's a solid?
Because it lights up the shape, hold it. It has a shape, a definite shape.
Has a definite shape. So, what does that mean, a definite shape?
Like, if you put it in something, it won't take the shape of that.
So it keeps its shape.
It keeps it.
All right. So definite shape, which means it keeps its shape. Right? Keeps its shape. That's the observable behavior. Now, what is the model for that behavior?
That the molecules are compact in a shape.
Okay. Is it enough to be compact?
Yes.
Suppose I compact them way down, but they're still moving around each other. Is that a solid?
Yeah, they're sliding.
Would that be a solid if they're sliding around each other? That's a liquid.
Yeah, I'm talking about they vibrate.
Ah, okay. There you go. So, for a solid to be a solid, the particles are stuck in place, but they can vibrate, right? So they're rocking and rolling, but they're not moving around very much. Huh? What'd you say? How about we say it this way? Particles wiggle, but stay in place. All right? They wiggle, but they stay in place. Kind of like you guys. You're all moving around in your seats a little bit. Yeah? Logan over here showing you. Fred's showing you. He's wiggling. Okay? There you go. All right? But you're staying in place, right? In your desk, you're staying in place. But you can move. You can twist sideways. With them over here, twist it sideways. All right? Got it? But you're not moving in physical proximity to anybody else. You roughly stay the same distance apart. You roughly stay in the same position relative to everybody else, but you might twist around some. That make sense? All right. So that would be describe why it is that solids have this definite shape. Got that? All right. Now, what about liquids? What do we observe about liquids that make them liquids? What do we see about liquids that make them a liquid?
The shape is like changed and diluted, so it doesn't have a shape.
So if I blow up a balloon with gas, isn't that gas also taking the shape of the container?
Yeah.
So what's the difference? We don't want the same definition for gases and liquids, do we? So we need to refine our definition so we can have a difference.
It takes up more space.
Gases take up more space?
The weight.
Liquids are more heavy?
The weight.
Heavier?
Yeah.
Okay.
How would you put that in scientific terms?
I don't know. How would you put it in scientific terms?
It's volume. It's not volume.
Well, just in terms of taking up the shape of its container, how would we differentiate just that definition part of it in the behavior of liquids taking the shape of the container and gases taking the shape of the container? How can we tweak that a little bit so those we can still use shape of the container but make it different for gases and liquids? A practical, useful, anybody can use it, even a third grader definition. Okay? No? A practical, simple definition. So I put a gas in a can. Doesn't it take the shape of the can? So what's the difference between that and a liquid? Think about, huh? You can't define a gas as it's a gas, okay? Here we go. Now we're getting there. All right. So she says you open the cans and the gas goes away. So what's the difference between the way the gas takes the shape of its container and a liquid takes the shape of its container?
If the liquid takes the shape and open it, the liquid won't go away.
So liquids will take the shape of the container even if it's an open container. Is that right?
Yeah.
All right. So let's see. There we go. And see, you guys knew this stuff. You just had to kind of think it through a little bit, okay? I'm training you to think like scientists here, all right? All right. So it takes the shape of an open container and takes the space available, but only in 2 dimensions. Well, really not even 2 dimensions. It takes, as long as it's going down into the side, it'll take the shape of its container, right? All right. So let's see if we can put that into some kind of words that make a little more sense than that, okay? So let's see. Well, not so much scientific because this is more of a third grade definition, okay? Takes the shape of a container downward and to the sides. How about that? Does that make sense? So then gases, what can we say about the way we define gases so that we can talk about it taking the shape of a container?
Like the particles are more free.
Okay, well, particles are part of the model over here. I want to talk about observable behavior that we can talk about a gas. What can we say?
Gas takes shape of closed container.
Ah, there we go.
You can put the closed in all caps.
Okay, I can do that. Takes the shape of an enclosed space.
Yeah.
You can say that. But closed container works good. Closed container. I underline it instead of capitalize it, okay? You can capitalize it. Okay? In all 3 dimensions. How about that?
That's not third grade.
Up, down, side to side. Back and forth. That's your 3 dimensions, huh? Yeah, you're right. Probably 3 dimensions is probably a little bit more than third grade. But, you know, I don't know. Third graders get pretty sophisticated. They play these video games, you know. They don't?
No, my niece learns about rounding and she's in the 3rd grade.
My son's in the 3rd grade.
All right. Let's not go there. All right, so let's talk about the model. What do we think is going on with the guys, please. What do you think is going on with the particles? The structural, you're going to hear me talk about structural particles a lot in here. Structural particles are the things that make up our substances down to the smallest particle. Okay? So that'd be atoms, molecules, ions. When I say structural particles, I'm talking about the building blocks of our substances. Atoms, molecules, ions. Okay? We're not getting down to subatomic particles. We're talking about atomic or those particles that atoms build together when they bond, like molecules, like ionic compounds and things like that, okay? So those are what we're talking about when we say structural particles. Yes, ma'am?
What is the difference between atoms, particles, and molecules?
Okay, atoms are the smallest unit of an element, okay? molecules are made of more than one atom bonded together by sharing electrons. Okay? But they have to be discrete particles. So you can have bonding together by sharing electrons to make actually crystals. The difference is that molecules are discrete or separate particles formed by the atoms coming together and forming these bonds by sharing electrons. Ions, on the other hand, are atoms or molecules that have more electrons than protons or vice versa. So they have a charge, and then that becomes a structural particle when they stick together because of their opposite charges. We'll get to all that. Don't sweat it yet. Some of this you learned, you didn't learn about, you shouldn't have, you probably didn't learn about polyatomic ions, but you may have heard about ionic bonding, okay? You may have learned about atoms forming ions when they have a charge. You may have learned that. We'll get into more complex stuff in this class, okay? All right, so what can we say about the model, the cause of this behavior we can observe?
Like, they kind of move freely, but not like two squad.
Actually, it's better to say. That's not bad, and that may be what you've been taught before. But here's what I'd rather you understand at this level. For the most part, liquid structural particles still touch. They just move around each other. Liquid particles are still touching like the solid particles are still touching, but the difference is the liquid particles move around each other. Okay? So the particles move around each other, but still touch. Okay? So, you might think of, I don't think anybody knows what a mosh pit much is anymore. You know what a mosh pit is? Okay. All right, so if you guys are structural particles, okay, in a solid you'd be like in these desks, you're in one place. You can wiggle around, move around a little bit, but you stay kind of in place. That makes sense? You're a solid right now. But now, if we get the music going, and you're up and moving around and dancing, and you're moving around each other, that's kind of like a liquid. Okay?
We go in the hallway.
Yeah. Okay. Got it? All right. So that's what a liquid is. All right. Now, what's the difference between that, where the particles are touching and moving around each other, and a gas?
They don't touch.
They don't touch. It's like the party's really going, and something's happening there that shouldn't be happening, and the cops show up.
And everybody starts running.
They scatter. Okay, so the particles of a gas, except for bouncing off each other and bouncing off the side of the container, they don't touch. All right? Okay, let's see if we can describe that then. Shh. Particles move away from each other and don't touch except for bouncing off each other. How about that? All right. Could a third grader understand that? Maybe. How about fifth grade? Oh, come on. Fifth grader could, really?
It just depends on what level they are.
Okay.
It just depends on if it's, yeah.
Okay. All right. Yes. I'm going to give you a practice test in a minute. Now, before I do that, I want to go back to those terms amorphous and crystalline. Okay? And I want to turn off my video capture because I'm moving around here.